Hi class, this is Mulhall and Trunkel over here, and we're going to show you how to do the quantized conduction in a gold wire experiment. So I'm going to talk a little bit about the background of it. So this is a sample. We have a piece of steel and some cigarette paper wrapped around it for insulation. And you can't see it on the camera, but finer than a hair is a piece of gold wire. What we're going to do is we're going to put a battery, we're going to put a resistance in series with this gold wire, and we're going to put a battery terminal, we're going to put a 5 volts across it. When those 5 volts goes through it, there'll be a very small current. This will be a large resistance, so there'll be a small current. The small current's going to go through the resistor, and it's going to go through the gold wire. The potential drop across the resistor is going to be I times R. That's going to be the biggest. So there's going to be a 5 volt drop across the big resistor, and practically nothing across the gold wire, because the potential drop across the gold wire is the current times the resistance resistance is nothing. Then what we're going to do is we're going to mechanically break the gold wire right here by pushing on the spring. Push, 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 it'll break. We'll do it really slowly with a micrometer. As soon as it breaks, now you don't have a gold wire anymore, you've got air. The resistance of air is huge, and so the current will go to nothing, and the voltage drop across the gold wire will be the 5 volts that the battery is providing. However, on the way from 0 volts up to 5 volts, as you're slowly breaking this wire, the wire will become finer, finer, finer. It'll become so fine that electrons will go through one at a time. That's kind of what's going on, right? It's a little more subtle, but the physical explanation of what you see is well within your grasp by the time you're halfway through the course. So you put this in, and you get a voltage. The voltage is stepped. It's not smooth. It doesn't go smoothly from 0 to 5. It's stepped, and we look at these steps. We zoom in on them, and from these steps we can calculate. We can see that these steps are proportional to E squared over H bar, Planck's constant, and the charge of the electron. This is quantized conduction. It's very exciting. And now Nick's going to take us through the procedure of how you actually do it.
All right, so you're up on our Google site for this course. There's a very well-written procedure from Dawn Doris. She worked on this last summer, and we demoed it in Modern Lab last fall, and it worked out really well, so we're doing it again. So that procedure is going to tell you to do a bunch of things. One of the very first things that you're going to do in the procedure is make samples for the next group that's going to come in. So if you're the first group doing this experiment, you're going to have them ready to go. They're going to be somewhere here. We'll make sure that they're there. So that's setting up, you know, the gold wire here with the epoxy. All right, you're going to have samples for your experiment, but you have to make some for the next group. So there's very clear instructions on here, but I just wanted to tell you one thing. There's going to be an instruction where you're going to take a razor blade and zoom in on this very small piece of gold wire that's between the 2 bits of epoxy. That's going to happen on the microscope over there. All right, so be careful when you're holding the razor blade under the microscope near your fingers. We don't want you to get cut. But what you're going to do is you're going to want to make a very small score into the piece of the hair-sized gold, all right, because that's going to enable us to get a very small piece of it as we bend it in the actual apparatus. So if you come down here to the apparatus, it's nothing really special here. We have a micrometer knob here. All right, so we have our micrometer, so you're going to see that the piece of steel that has a gold wire epoxy to it is being pressed against by the micrometer ending here. So when I rotate this, that end pushes on the steel, and that goes ahead and bends the gold wire until it breaks. So what you're going to eventually see on the computer is a voltage versus time graph. And when you break the wire, you're going to see that voltage jump up to your maximum voltage. And I think we have it set at 1.5 volts. All right. So what you're going to want to do is turn that micrometer. Don't worry about how fine you do it until it breaks, and then back it off slowly, just so that it goes back down to 0. And then we'll have a nice circular piece of plywood here, so that's going to allow you to turn it very finely in order to see the jumps on the voltage versus time plot. Now the procedure tells you what to do with that voltage data. You're essentially going to be then making a second plot of something called conductance, which is the inverse of resistance versus time, and that's going to have, they're going to be proportional to E squared over H bar. So each of your steps should correspond to N equals 1, 2, 3, however many steps you get in terms of E squared over H bar. And I think that's it. Do you have a scientist?
We have yeah, we do, because again, J.J. Thompson.
Oh,
hard to beat.
Hard to beat, yeah. All right, I think that's it. See you later.